Okay, so we want to determine if this equation is exact and solve it if it is. So this problem is kind of confusing for two reasons. First of all, it's got brand new variables in it, so it doesn't have our x and y that we know and love. The other thing is it's got a little bit of a trick in there that throws a lot of people off. So before we go ahead and dive into this problem, let's remind ourselves of our form that we're supposed to have. So our form that we've seen so far in this section is m of xy, some multivariable function, plus n of xy, another multivariable function, times dy is equal to 0. And again, there's some very important things to watch out for here. First of all, it must always be equal to 0. But another thing you notice is there's a plus sign between these two terms here. And you'll notice that our problem up here does not. So if we were to take this and write this over again in different variables, it would be m of r comma theta dr plus n of r comma theta d theta is equal to 0. And now if we take our equation, which is cosine of theta dr minus the quantity r sine of theta minus e to the theta d theta equals 0, you will notice that the sign is wrong. So when we write it over again, we have to make sure we incorporate that minus sign into the term. So writing it over again, this is going to be cosine of theta, which is your coefficient on dr, plus now negative r sine theta plus e to the theta times d theta is equal to 0. So this right here, this cosine of theta, is your capital N, and then this term back here is the capital N. Again, don't fall into the trap where you have that minus sign there and you forget to relabel this. So now let's go in and take our partial derivatives. So again, remember, the first one is taken to the other variable. So this is m sub theta, or the partial with m with respect to theta. And that's equal to the negative sign of theta. Then we need to take n sub r, which is the partial of n with respect to r, and that partial is going to be negative sine of theta as well. Because again, the e to the theta term is canceled out to 0 by the partial derivative, and the r becomes a 1 when we take our derivative. You'll notice right away that, these are equal. So our equation is exact, which is great, which means we can solve it using the methods in this section. So to recap, we now want to build a function, capital F of r comma theta equal to c, that makes the above partial derivative conditions true. So to find the f, we're going to go ahead and take the first coefficient and integrate it with respect to r. So that's going to be the cosine of theta integrated with respect to r. And that's really easy because that's just a constant. So we're going to get r times the cosine of theta plus some unknown function g of theta. Okay, so the next thing for us to do is find this function g. And to do so, we're going to take the partial of f with respect to theta, and that's going to be negative r times the sine of theta plus the ordinary derivative g prime of theta. And again, we set that equal to the n, which is negative r sine of theta plus e to the theta. And again, these cross terms are always going to match. So we can essentially cancel them out, and we get the equation g prime of theta is equal to e to the theta. A quick integration tells us that g of theta is equal to e to the theta as well, plus some constant k. So now when we build our function back, we're going to have our f of r comma theta is equal to our r cosine of theta plus our g, which is e to the theta, plus a constant k, is equal to capital C. And again, in the solution of a first order equation, you never have to have two unknown constants. You can just absorb one into the other. So we'll just kind of strike out this k, and then our solution is going to be r cosine of theta plus e to the theta equals some unknown constant c. And that is the solution of that exact differential equation.